Well, all right, so back to physics component of geometry, topology, and physics. Let me recall the context we've created during the last two classes. So we have Lagrangians, which are N0 forms on the product of the space-time in the space of fields. So there are those variational forms which are n-1 forms on the same space. So we have the key equation dl equal to d gamma plus q delta phi dnx. Up to now, that's the main equation that we have. Q are Euler-Lagrange equations. And last time we introduced the concept of a symmetry. So there is a Lie algebra acting on the space of fields. And the condition is somewhat complicated. We're saying that the Lie derivative of the Lagrangian is exact on the space-time. So the condition says the existence of those alpha of xi's. So maybe I should make it also precise, the bookkeeping. So this alpha is supposed to be an n-1 0 form on M cross F. Maybe one thing that we were missing last time, and I think that's essentially why we failed to prove one of the theorems. So we should make more precise the properties of symmetries. And there are different ways how one can formulate it, but let's do the following. We say symmetry is local if it doesn't change the support of a field phi. So a field phi is a map from M to some vector space V, and it may have some support where it is non-zero, and we want this support of the field on which we act by our vector field to be contained in the support of phi. Essentially, we'll see that typically we'll have those vector fields to act by some kind of derivatives on phi. And of course, derivatives don't change support. But in general, you can imagine some non-local actions where, for instance, this guy would depend on phi in a very different point. So, and that would violate this property, and that's probably not good for us. OK. So let me recall that last time we stated the following theorem. So the quantity j of psi, which is a finite combination of gamma and alpha, satisfies the following equation. So d j of psi on solutions of EL is equal to 0. So that's the second important equation or important fact we obtained, or rather we will obtain in some minutes from now. So these are up to now like two major equations we have. I'm not quite sure whether I said last time about the terminology. In literature, sometimes such equations are called continuity equations, so d of something equal to 0, or sometimes one says about this equation that j of psi is a conserved current, whatever that means. That would be more like a physics lingo. But of course, for us, just the de Rham differential of this j is equal to 0. Now, proof. So the proof is very easy. So as I say, basically what we have is this equation, right? So we don't have much else. So let's apply iota of psi f to this equation, and let's see what comes out. So iota psi f applied to dl. Well, in fact, by the Crotan's magic formula, right? So iota psi delta plus delta iota psi is the Lie derivative, but delta iota psi applied to this guy is 0 because of the degree reasons. So this is actually L psi f L. Well, and we assume that we have a symmetry, so this means this equation is satisfied. So this is g alpha of psi. Well, on the other hand, we can apply iota of psi to the right-hand side. So this gives iota psi f d gamma plus q iota psi f delta phi dnx. So here these are two odd objects, iota of psi and d, even though they act on different parts of our de Rham complex. So iota of psi acts on forms on f, and d, straight d acts on forms on m, but still they anti-commute because they are odd. So we get minus d iota psi f gamma plus q iota psi f q delta phi dnx. And this gives us the following equation. So d of j of psi, this is equal to d iota psi f gamma plus alpha of psi plus the term with q. And this equation is valid where? It's valid in, I think, omega n0 mf. Is it right? I think it is, yes, I think it is omega n0 mf. Now, well, inside this space is sitting omega n0 m sol el, and sol el, that's just the locus where q is 0, right? So this is the q equal to 0 locus. So this means that if we restrict dj of psi,
I'm sorry.
yeah.
dj of psi is equal to this q bearing because it's written that dj of psi is equal to dj of
Oh, yeah, right. You're right. Yes. Yeah, this is, that's right. This is equal to this. Yeah, thanks a lot. But so it's rare you can reconvert the wrong equation into a right equation so easily. Okay, yeah, that's that's the correct equation. Right. So this means that if you restrict it to m times sol EL, we get 0. So here it was a little bit sloppy, so one restricts it to m times sol EL. And this is an equation. This is an equation in this space in omega n0 m times sol EL. I hesitate a little bit to call it the Nurser's theorem, but this is closest to the Nurser's theorem that we have in the course. So let's still say, so this is the Nurser's theorem. Does it look similar to the Nurser's theorem you had in the quantum mechanics course? So I'm not. That's why I'm not sure it's exactly similar, but okay. So let's give some examples. Maybe before I give examples, let me recall a piece of notation we had last time. So when M, the space-time, is a segment or possibly a real line times a manifold sigma. Sigma has no boundary. So then we introduce the notions of charges. So the charge is an integral of J. So J is called a Noether current sometimes. So current. So the integral of J over sigma is a charge, and it is conserved. So this is a function on sol EL, and we showed last time that you can compute it at any time slice, or even more generally at any reasonable sigma which carries good Cauchy data, and it's independent on this choice. So it's actually a function on sol EL. Well, I think it's a high time to give you some examples, especially like we are torturing you a little bit with exercises, because I think kind of now I will explain things that you probably need to efficiently do exercises which come just in the problem set 2. So sorry for kind of maybe giving you too complicated material in the exercises. So I would like to spend some minutes on discussing again vector fields on the space of maps. So recall that the symmetries, we decided in all this story of the Noether's theorem, the symmetries, they are special vector fields on the space of maps, on the space of fields, which have good properties. But first question, how do you practically build vector fields on the space of maps? So let me, before going into vector fields or Lie algebra actions, let me start with group actions on F. So this is somewhat more intuitive. Oops, sorry. Okay. Right, so this is somewhat more intuitive. So recall that F, these are maps from the space-time to the target space. And let's assume, to start with, that you have a group action on the target. So this induces for you a group action on F. Well, by an obvious formula, so you take your map, phi, you want to act on it by group element G, so this should be a new map. So what is this new map? Well, take a value of phi at M and act on it by the group element. So the same game can be played if you have an action on the space-time. If you have an action on the space-time, then again, the group acts on the space of maps. And here the formula will be slightly different. So here, how is it? I'm always confused with those plus and minus signs, so left and right actions. I guess you should act by G minus 1, or maybe that's the other way around, who knows. But I think you're all highly qualified and accomplished mathematicians. You should be able to figure out what, but okay, I cannot. Right. Let's say it's a working guess. So now this picture induces for you Lie algebra actions. And so Lie algebra actions would be as follows. We just need to differentiate those group actions. Assume that the group is a Lie group. So then this would induce for us some Lie algebra actions on our space of fields. So what will be the formula here? Let me write it in the following way. So I have psi, an element of my Lie algebra. And so in the first case, so I will have psi f acting on phi at M. So I should just differentiate the right-hand side, right, for the group element, which is the exponential of t psi, acting on phi at M at t equals 0. Well, this is simply called the action of this Lie algebra element on V, on phi, computed at M, right? So that's just the definition of the action of the Lie algebra on functions. It will be slightly more complicated in the second case. So what will happen here? So I write d over dt, phi exponential minus t psi acting on M at t equals 0. Well, so this will be just a chain rule from calculus. So this will be dm phi, the differential of the map phi at M, composed with the action of minus psi at the point M. Perhaps here I should make it a little bit more explicit what it means. Now psi at the point M, it's a tangent vector, right? It lives in the tangent space to M at M. Now dm phi, so this is a map from the tangent space at M to the tangent space to phi of M of V. But V is a vector space, so the tangent space is just canonically isomorphic to V itself. So this means that this thing is an element of V. And so this guy is a function on M with values in V, as it should be, right? So that's a tangent vector. So you see, these are basically two ways how we can practically build tangent vectors to the space of maps. Of course, there are many more. There are many other tangent vectors, but that's the tangent vectors which are easily accessible to us. Once you have a vector field on V, you can build a vector field on the space of maps. Or if you have a vector field on M, you can also build a vector field on the space of maps. So these are two easy things to do. Right. So now let me give you examples of symmetries and of Noether currents and of charges. So let's see how this machinery works in practice. So let me choose as a first example, so the scalar field the scalar field on R to the power n plus 1. So strictly speaking, it doesn't quite fit the context that we want to consider, because here that's a product of R, which may be the time axis, and some non-compact vector space, Rn. So maybe instead we want to look at R times a torus of dimension n. So this would, strictly speaking, fit better. Even though playing with conditions on our fields, we can also do this. So we take a scalar field. V is simply equal to R. So we consider the Lagrangian, which is the most standard. So the Lagrangian of the scalar field. And now we should choose what is the symmetry. So I will introduce a vector field on V. And I will try to generate a symmetry. So let me call the coordinate here by y. And let me say psi is simply d over dy. So the corresponding group, this would be translations on the target space. So the first question is, what's the corresponding vector field on the space of fields, or on the space of maps? It is described by this formula. So let me so psi f phi at M. So this will be the function psi f acting on phi at M. So what is the action of this vector field? So this phi is simply a coordinate, right, on this real axis. So you take a derivative, the first derivative of your coordinate. So it's d over dy of y. So this is simply equal to the function 1, which depends on M, but which doesn't depend on M, right? So psi f phi of M is simply equal to 1. viewed as a constant function on M. Right. So now the question is it a symmetry? Well, let's apply this this derivative to, or this vector field to L. Well, what I should do, so I differentiate every phi, and phi becomes 1 when I differentiate. But now all these phi's, they enter there under a derivative with respect to some spatial coordinate. And here it's a constant function on M, right? So I can, of course, write down the answer, but all the terms will be 0, because everywhere you will have some derivative of 1 in every term. So this is actually simply 0. This means that I can choose alpha of psi equal to 0. Remember, there was this whatever unpleasant story of alpha of psi. Now, okay, alpha of psi is simply 0, and I also conclude that this is a symmetry. This is a very simple symmetry, but this is a symmetry. So nothing happens to the Lagrangian when we apply this vector field. The Lagrangian does not change. Now, to write down j of psi, I have to write down gamma. Gamma, it's a kind of complicated story. Let me do the following. Let me write one term in gamma, and then you complete the other terms if needed. So I think gamma starts with the following term, minus d naught phi delta phi. So that's when I take a derivative with respect to d naught phi, and then here it will have, sorry, here I should have written dn plus 1 x, right? And here I will have dx1, dxn. So the dx0 is missing. Plus, there will be other terms. So there will be terms with other di phi's and with other one forms missing in the wedge product. Right. Now, so j of psi will be simply the contraction of gamma with this vector field. And as you see from here, right, it's very easy to contract. When you contract with delta phi, you just get 1. So this will be minus d naught phi dx1 dxn plus some other terms. And finally, the conserved quantity q. So that's an integral over sigma of j of psi. And I would like to, so this is my 0 axis. And these are all the other x's. And I would like to choose my sigmas to be simply equal time slices. So q is an integral over sigma, and this is an integral of d naught phi times dx1 dxn. Notice that this formula is correct. All the other terms, they're not going to contribute because there one of the dxi's is missing. So actually, that's why I permitted myself not to write the formula in such a detailed fashion, because all the other terms, they don't contribute in the charge. Now, so let me ask you a test question. So this charge is conserved, right? So that's what a corollary of the Nurse's theorem says. So the charge is conserved means dq over dt on sol EL, it's supposed to be equal to 0. So what are the equations? What are the Euler-Lagrange equations in this case? Could you recall me for the scalar field? What's the in a Minkowski space? What's the Euler-Lagrange equation? So by now that we need to know by heart, kind of. The wave equation, right? So the EL equation, that's the wave equation. D naught square phi minus Laplace phi is equal to 0. And in principle, our theorem or our corollary says that this should imply, right? So in practice, so now that's a concrete example. So this should be true. Of course, if we want it to be really precise, if we don't want to think at the conditions at infinity, we should think of a torus. Or if we want to think of r to the power n plus 1, we should impose some conditions on our phi's. We should say, for instance, they are compactly supported. So that's a small test question for you. Just try to check it. Does it actually follow, right? The whole machinery that we set up guarantees it has to follow. But now, kind of, is this thing conserved? It better be, right? So try to think about it. So how does it work in practice? Let me do one more example of the same type. So it's again m being Rn plus 1, or kind of better, perhaps R times an n-dimensional torus. And now I'm going to take V to be complex numbers, but we always considered all our vector spaces over R. So we're going to identify it with R2. And so sometimes in physics you would have the following words. We know if V is equal to R, we say it's a scalar field, right? Or physicists say it's a scalar field. So this is, that's they call a complex scalar field. So maps with values in R2 that we can identify with C if you want. So the Lagrangian going to be rather similar to what I wrote before. The only thing is I will write absolute values squared instead of squared. So sum from 1 to n dl phi squared. What about the symmetry? So let me start with a group action. I'll start with a group action on V, and that's something that we saw a lot in our symplectic geometry course. So we look at the action which simply sends the coordinate z to exponential I theta z. And of course, if we write for the complex conjugate coordinate z bar, it will be sent to minus I theta z bar. Well, what's the corresponding vector field? In those complex coordinates, we can write it as I z over d over dz minus z bar d over dz bar. Of course, you can also write it in real coordinates if you want, but perhaps it's easier to write it in complex coordinates. Well, there will be the corresponding vector field psi f. It acts on phi. And what it does, right? So phi is like z, right? So phi is a pullback of z to the space-time. So it gives you I phi of m, right? So when you act on z by this vector field, you get I z. So when you act on phi, you get I phi. Is it? So similar, psi f phi bar of m is minus I phi bar of m. So phi bar is like z bar. Maybe I should say here that maybe somewhat strangely, let me write it this way. Of course, on the right-hand side, I use phi as a map, and here I use phi as a function on m. So roughly speaking, that's how it works. All right, so let's now apply L psi f to L. Perhaps I do the computation for the first term, and I don't do it for other terms. So what will happen? So this is L psi f, and here let me write it down explicitly, 1/2 d0 phi bar minus other terms. Well, so what will happen here? So psi f differentiates phi. It gives I phi. So it will be I d0 phi bar. Sorry, I'm writing phi in different styles. But then it will also differentiate phi bar. It will give minus phi bar. So minus I d0 phi bar minus other terms. So these terms cancel. And the same will happen with all the other terms.
Do you assume phi is holomorphic here?
No. Absolutely not.
But then how can you in general have something as simple as I phi m? So you don't understand.
Why not? Why does it have anything? Even it's not completely clear what does it mean holomorphic. M is not a complex manifold, so like it even does not make sense, right? Yeah. So what I'm doing? Recall, I have a map from M to V. So now I have a vector field on V. I wrote it in complex coordinates, but I could have written it in x, y coordinates on R2. Right? So I have this vector field. So now I have a map from M to V. And I am composing, one can say, composing this map with a vector field on V. So this gives, that's one of the ways to obtain a vector field on the space of maps. So that's what we were discussing before. And that's actually what I'm doing. Right? So that's just the composition formula that we had before. Right. So you see, good news. This is equal to 0 again. So this means alpha of psi is equal to 0. So let me finish this example before the break. So now what about the current and the charge? For that, unfortunately, again, I need to write down gamma. So let me again write down only the first term. So I think the first term will be minus 1/2 d0 phi d0 no delta phi bar plus d0 phi bar delta phi dx1 dxn. I hope I computed it correctly, but by now I think you're probably better specialists of those gammas than I am. So I computed, let's say, I computed the gamma according to our recipe, and that's what I got, plus other terms which contain other dx1, dxn's. So now I need to, so j of xi is simply iota of xi f gamma. Fortunately, that's a very simple computation, so I'm simply applying it to those delta phi's. So I'm getting 1/2, and here I'm getting phi. No, I'm getting what? Phi bar d0 phi minus phi d0 phi bar dx1 dxn plus dots, dots, dots. And now the charge is I over 2 integral over sigma phi bar d0 phi minus phi d0 phi bar dx1 dxn. Again, all the other terms disappear. So you see, kind of course, here perhaps it doesn't tell you much, but okay, that's supposed to be a conserved quantity. So its conservation should follow again from the early Lagrange equations of this simple Lagrangian. It already looks a little bit more sophisticated. Before it was just an integral of some derivative of phi. Now it's even a quadratic combination. And I think this already would have some interesting meaning in physics. That's probably related to the theory of superfluidity or superconductivity. So this would be already a meaningful physical quantity in some theory which has applications. The one before, it was not very interesting. This one is already an important and interesting physical quantity. Right. Okay. So let's have a break, and after the break, we'll look at the situation when alpha perhaps is not 0. And this typically comes up when you try to act by symmetries on the space-time. You see, up to now, we were acting on the target space. The question is, what happens if we start working with space-time? All right, let's continue. So I would like to show you one more example. And in this example again, M is R m plus 1. V is R. So that's a scalar field. The Lagrangian is the standard Lagrangian of the scalar field. Now, what about the symmetry? So I would like to, here as usual, the usual disclaimer that probably it's better to have R times Tn or take care of the support of the fields. Right. So I would like to now introduce some action or some vector field on M instead of a vector field on V, and generate a vector field on the space of maps using that. So let's say psi M will be just a partial derivative in the time direction. So the corresponding group action would be translations along the time axis. So the corresponding vector field on the space of fields. So let me recall the formula. So the general formula was dm phi composed with minus psi, or computed on minus psi m. So what does it mean in practice? We take a differential of phi and compute it on the partial derivative in the time direction. So let me give you an answer. So this is simply d naught phi of m. So the differential is a gradient vector of phi, and you compute it on psi m, which is the first unit vector in the standard presentation. Say you identify the tangent space with Rn plus 1, then this vector is 1, 0, 0, 0, right? You compute it on, so let me perhaps write it more explicitly. So this is a product of d naught phi, dn phi times 1, 0, 0, 0, and here minus 1, right? So that's an explicit writing in the first year calculus. Right. Okay. So the question is it actually a symmetry? So let's apply Alekseev F to L. So now let's discuss what's going to happen. We're going to apply this vector field to every phi there. And well, every phi will be converted to minus d0 phi. So this means the following. Let me again denote it by straight L. So the answer will be minus d0 of straight L, right? Because you apply a derivation which is just minus d0 on everything. dx0, dx1, dxn. So notice that this time it is actually non-zero, right? Before we were applying our vector fields on the space of maps to our Lagrangians, and we were typically getting 0. But now it's actually non-zero, and that's why we had this elaborate notion of symmetry. The symmetry was not necessarily something which is killing L, but maybe it gives you an exact form. So is it an exact form? Well, let me write it in the following way. This is d of minus L dx1 wedge dxn, right? So this seems to be a correct equality. You apply d to L, it will compute, of course, derivatives in all directions, but since it's only dx0 which is missing in my form, only the d0 derivative will count, and then that seems to be a correct equality. So that's my alpha. Okay. So what about gamma? I think we already wrote the gamma for this situation, but now maybe should we write it in a more detailed form? Maybe not. So gamma is equal to minus T naught phi delta phi dx1 dxn plus dots. I think that we already had today. So what about the current? So the current J of psi is now iota psi f gamma plus alpha. So I make a substitution, so delta phi becomes minus d naught phi, and this gives me d naught phi squared dx1 dxn plus dots plus alpha, and alpha is this guy, so minus L dx1 dxn. Now, what is Q? That's an integral of a sigma of J of psi. And of course, these dots terms, they will cancel. And I will have an integral here, d naught phi squared minus L, 1/2 d naught phi squared plus 1/2 sum over I, di phi squared dx1 dxn, or perhaps I rewrite it in a more conventional form, and here I will have sum from 0 to n di phi squared dx1 dxn. So that's the conserved charge. So this conserved charge you probably heard of a lot, starting from your physics course in high school. So this is called the energy of the system. And but for us, you see, it has the same standing as all the other charges, right? Let me recall again our picture. So we have Sol EL. We assume that it is isomorphic to the space of fields that we defined on the time slices. So typically here we have maps to R, so we can call them Q of t. So evaluation of the charge on a given time slice, like something given by this formula, right? It's defined on a time slice. And since they all coincide, right? The charges are time independent, right? That's what the corollary of the Nurse's theorem says. This means that the charges are actually defined as functions on Sol EL. So they are independent on the time slice that you choose. And perhaps I recall again this picture. So that's our cylinder, sigma, the time axis, A and B. So you can compute charges on time slices, or you can compute charges on all reasonable surfaces which support Cauchy data. So here, of course, the details of the theory enter the game when you want to say explicitly what it is, but anything which is sufficiently transverse to the time axis and which supports good Cauchy data, there you can compute your charge. Right, so that's a very, very beautiful picture, and maybe I would like to stress again, this picture is somewhat unexpected when you first start thinking about Lagrangian about this kind of definition of classical field theory that we started with. Now, in the remaining half an hour, I would like to reprove or prove the theorem that we failed to prove last time. And I would like to talk towards the end about the relation between the two forms. Recall that on Sol EL we have a two form and the charges. So these are so recall we had this theorem. It was saying that suppose we have a symmetry of our field theory. Let me add local because that's what was missing last time. So then the EL equations are preserved by the symmetry. So if Q is 0, then the vector field is tangent to the surface of EL. So here is the proof. Well, we only have one formula, right? Essentially, that's the only thing that we can use. There is not much else. In the last proof, we applied the contraction iota of psi f to it. Now also, in differential geometry, there are not that many objects that we can apply. Let's apply now the Lie derivative to the same equation. So so first the left-hand side. Lie derivatives commute with de Rham differentials, so I can change the order. Now we assume that this is a symmetry. This means that this will be G alpha of psi. So the two partial de Rham differentials, they anti-commute. So we can rewrite it as G delta alpha of psi. On the other hand, so this is L psi f d gamma plus L of psi f q delta phi dnx plus q L of psi f delta phi dnx. And maybe the only thing we want to do here is exchange the de Rham differential on M and L psi f. Actually, so those commute. So this is even, this is odd, and this one acts on the space of fields. This one acts on the space-time. So this is actually equal to G. So now I would like to reassemble everything into the following formula. So I have D of delta alpha of psi plus L psi of gamma plus L psi f q delta phi dnx plus q L psi f delta phi dnx equal to 0. Right, so that's the equation that I obtain. Now let's apply integral over m to the left-hand side. So this will give us the integral over the boundary of m, delta alpha of psi f, plus L psi f gamma, plus integral over m, L psi f q delta phi dnx plus integral over m q L psi f delta phi dnx, and this is equal to 0. Now let's do the following. So this is inequality now which lives where? I think it is, it lives in 1 forms on f, right? So m is no longer there because we integrated over m. We did a fiber integral in the product m times f. And this is a 1 form, visibly. This is a 1 form on f.
I'm sorry, we didn't write like the variables over which we integrate dm.
Sorry?
We didn't write over which variables we integrate dm, like the first 7. It's over dx or whatever. The first.
Oh, this, let's say m is a manifold with a boundary. We don't know. Maybe there are boundaries in different directions. For instance, you can imagine whatever m is whatever sum, for instance, square or something. So there will be boundaries with respect to different axes. So then, who knows? So we'll discuss it in a second. Okay. But yeah, whatever this form is, it's integrated over the boundary. Okay. So now let's consider consider a vector field on the space of maps such that v of phi is equal to psi. Psi is a function from m to v. And let's assume that it's compactly supported away from the boundary. Now you see this symmetry, and let's say this left-hand side. Let me denote it in some way. What would be a good letter? Sigma. Now I'm considering iota v of sigma. Well, because my symmetry is local, this implies that this term will actually vanish when I apply iota v to it. Because psi vanishes on the boundary and some neighborhood of the boundary, so this thing will be 0. It will not see it. Now, there will be this term, L of psi f q psi dnx, plus there will be this term, iota v L And this is equal to 0, right? Because sigma was equal to 0 to start with. So this expression is now a function on f. So this 0, which is equal to the sum of two contributions, is a function on f. So inside f, as usual, is sitting sol EL. And we can restrict our function to sol EL. So what will happen? Of course, this term will vanish on sol EL because q is 0 there. So this term will remain. Sol L is equal to 0. But now we see that the pairing of this expression with an arbitrary map psi, which is compactly supported away from the boundary, is 0. So then, whatever, up to some small functional analysis, so this thing has to be 0. So there is no way for it to be non-zero. Is 0 on solid L. Here, I think it is essential that we now assume locality of the symmetry, because otherwise you see this term, if the symmetry were not local, even though you integrate here over the boundary, but maybe this term would be non-zero when we pair with psi. If here we allowed to kind of, with our symmetry, move something from the bulk, maybe then these non-vanishing values of psi would contribute in this term. But now we assume that this is not possible. So let me make one remark. So now on solid L, this term is 0. We proved that this term is also 0 on solid L, right? Now we have the following corollary. We have this one form, which is an integral over dm of delta alpha of psi plus L of psi f gamma. So this is an element of omega 1 f. Now let's restrict it to, oh, maybe that's, no, okay, right. So that's an element of omega 1 f. Should I still call it sigma? Maybe let me call it sigma tilde. Right? Only the first term. Only the first term. So we take iota v sigma tilde and restrict it to sol EL. Now we take arbitrary v, whatever it is. Doesn't matter whether psi is compactly supported or not. Like, let's take any psi. But we already know that this term is 0 and this term is 0 on sol L. This means that this has to be 0. Now for any psi, right? Now we take a vector field of this form. Now we take an arbitrary psi. we evaluate the pairing. Now this formula is telling us that actually this contribution, so this guy computed on an arbitrary psi, is 0. Let me continue this remark. Imagine that M has a boundary which consists of several connected components. So it's a disjoint union of some ni's. So then, sigma tilde is equal to sum over I of sigma tilde I, right? Because it's simply a sum of integrals over those ni's. Of this form. Well, we know that iota v of sigma tilde is 0. Well, now what we can do? We can simply choose our psi to be supported near one of the boundary components. So it's supported somewhere here, and it's 0 near all the other boundary components. Well, the same locality argument tells you that all the pieces, they have to vanish separately. So iota v integral ni delta alpha psi is equal to 0. Now for all v. But now if some one form is equal to 0 when paired to an arbitrary vector field, what is this one form?
0.
Right. So all these guys actually vanish. Of course, on sol EL. Right. Now I would like to use it. I would like to use this consideration to prove one more theorem. I think it's probably the kind of last theorem we prove in this topic. So next time we will do something else. And this theorem will make a close contact to what we did in symplectic and Hamiltonian geometry. So suppose we have G acting on F. Local symmetry. Q of psi is the corresponding conserved charge. So then there is the following formula. So the contraction of the vector field iota psi f with omega. Omega was the 2 form defined on Sol EL is equal to minus delta Q of psi. So you see, this is a setup of Hamiltonian geometry, right? So this is in general infinite dimensional Hamiltonian geometry. We've got our space, Sol EL. We've shown in the previous theorem that the action of G restricts to Sol EL because the Euler-Lagrange equations are preserved. We've got omega equal to the integral of a sigma d gamma, which is a 2 form on Sol EL. And we have, if we think of it depending on psi, a map from Sol EL to G star, Q of psi. And this is almost a setup of Hamiltonian geometry. The only thing here which is a little bit, or maybe there are 2 things here perhaps, let me say. So there are 2 things here which are a little bit in doubt, or which depend then on the concrete setup. So one question is a non-degeneracy of omega. So that, first of all, sometimes it's simply not true. So omega is certainly closed in this setup, even exact. But whether it's non-degenerate, it remains to be seen. At least we haven't proved anything to this effect. And if our situation is infinite dimensional, we should actually discuss what it means to be non-degenerate. That's also a somewhat non-trivial question. So the other question is, in the Hamiltonian geometry, we typically assumed that this map is equivariant. Now, this is by no means guaranteed. This may be true. Sometimes it's true. Sometimes it's simply not true. So, so you do get some kind of infinite dimensional Hamiltonian geometry out of classical field theory with symmetries. But this may be Hamiltonian geometry with defects or difficulties. So this may happen. So what about the proof of this equation? Let's simply look at the left-hand side. So our setup is a cylinder. So M is a cylinder, AB times sigma. And so that's what we have. So let's reshuffle iota and the integral. There, as you know, I'm not very good at computing signs. So there is possibly a sign. And let's use the Cartan's So that's the integral, sorry, over sigma. And let's use the Cartan's magic formula. Now, let me do the following. Let me here use the definition of the Noether current. So the Noether current is this thing plus alpha, right? So I can say that this is the Noether current minus alpha. One more bracket. And let me now reshuffle the terms in the following way. So this is plus minus integral over sigma L psi f gamma plus delta alpha psi. And here minus plus integral over sigma delta j of psi. So let me do the last rewriting. So this is plus minus integral over sigma L of psi f gamma plus delta alpha psi. And here I would like to reshuffle delta in the other direction. It will give another plus minus. Plus minus times minus plus, it gives minus. Because that's just the same sign as I introduced here. I brought in some odd object through this fiber integral. Now I'm bringing back another odd object in the other direction. So this is minus delta. Now see, so this guy is simply q of psi, right? So that's the integral of j. Now what about this thing? What about this thing? Well, what's the boundary of M? Well, M has two components of the boundary. It is sigma of A union with sigma of B. So let's choose one of those sigmas for these integrals. We know that it doesn't matter which one we choose. We can, for instance, choose sigma A, right? So we can say that this was always sigma A. Well, if you're sitting on at a point which is a solution of EL equations, and you take an integral of this thing over a connected component of the boundary, you get a one form which is equal to 0, right? So this vector is equal to 0 there. So this is a connected component of the boundary. Therefore, this is 0. So we get this equal to minus delta q of psi. So we've done things which were kind of maybe a little bit complicated for you at the level of formalism, but I think they are really very nice and surprising. They're probably most of you heard something like this already, but they're mixing several things, those variational calculus on the one hand, then you get EL equations, some kind of PDEs. So then you get two forms, sometimes symplectic forms. And if you add group or Lie algebra actions, you get conserved charges and this kind of Hamiltonian, sometimes infinite dimensional Hamiltonian geometry. So let me finish with two things. On the one hand, starting from the next lecture, we'll be doing different things. Like one thing which is on the plan to talk a little bit more on the situation when the target is not a vector space but maybe a manifold. So that's one thing. More important thing and a bigger thing, up to now we were doing classical field theories, but starting from the next class we will probably specialize to something which is called gauge theories. So gauge theories, which is something which is very much used both in physics and math, and we'll start looking into like specific type of theories starting from the next time. So that was one thing. So the other thing is Pavel Safronov, he wanted me to present one topic today which will be useful in the next problem set, but I failed to do it. So this means that there will be some problems in the problem set that you cannot solve, and then instead I want to give you some problems that you can solve, and the other problems that you cannot solve, they will postpone to the next problem set. So the problem set 3. So one problem that we saw today, that was this exercise. Show that Q so show that this charge is conserved on solutions of Laplace equations or of the wave equation, and let's say sigma will be g to the power n. So that's one question. And the second question is consider classical field theory with an arbitrary first order Lagrangian, and find the energy, which is the charge corresponding to psi, the partial derivative in the time direction on M. So we did this exercise for the very particular free field theory. Now figure out what this charge is in the arbitrary case. Okay, well, that's it for today.